Today we're going to discuss Rolle's theorem and the mean value theorem. All right, both are born from the extreme value theorem. So the extreme value theorem told us that if we're on a closed interval, there must be a maximum and a minimum value. Meaning that if I'm looking at a function on a closed interval a to b, there must be a maximum and a minimum value, right? So here we have f of a and f of b, and there must be a maximum somewhere on this interval. So EVT, our extreme value theorem, says there must be a max and a min on the interval a to b if f of x is continuous and defined everywhere on the interval. So what we're going to do today is think about turning the value theorem inward and using that to talk about characteristics of the graph inside of the interval given our endpoints. All right, so we're going to draw conclusions based on our endpoints about what the graph does in between. So this is going to tell us about the characteristics of the graph, but also the behavior of the graph on an interval. So before we were talking about overall y values on an interval, including the endpoints. Now we're going to be talking about the interior of the interval using some information from those endpoints at interval. So as your text states, we're turning that extreme value theorem, our focus from the outside back inside on a closed interval. So take a moment to write down Rolle's theorem. It says that if we've got a function that is differentiable on the everywhere on the interval a to b and has f of a equal to f of b, so the y values are equal at the endpoints, then somewhere in the middle the derivative must be 0. We have to have a critical point or a turning point, right? F prime of c equal to 0 means a critical point. Or in this case, it's going to have to be a max or a min. All right. So that's more specific than a critical point. All right. Because it's a turning point, we have to go back to the y value that we started at. So we know that there has to be at least one point C on that interval where the slope is 0, right? Because we have to turn around. So this first example here is going to illustrate that point. We have to find our x-intercepts for the function x squared minus 3x plus 2. X-intercepts come when our function, our y value is 0. So we're looking for when this function equals 0. If you factor, you'll get x minus 2 and x minus 1, where x minus 2 equals 0 and x minus 1 equals 0 will be our intercepts. All right. We have synonyms for that. X-intercepts are the same as saying zeros or roots, right? So a little blast from the past there with that vocabulary. So those are our roots. So if we want to just quickly sketch a graph of our function. Without any y values on it, it's going to look something like this. So we're interested in the interval from the two x-intercepts. So that's like saying A and B are 1 and 2. You'll notice that our y values there are the same. They're both 0, right? Which is the first condition for our Rolle's theorem. It says that they have to be equal, right? Our y values have to be equal. The function has to be differentiable all the way throughout. We don't have any cusps, corners, or vertical asymptotes. I'm sorry, vertical tangent lines. So we're differentiable in between. So now we're ready to figure out, okay, where's that turning point? So that's going to happen when our derivative, which in this case would be 2x minus 3, equals 0. Because our slope at a turning point, a maximum or a minimum, is 0. So when we solve that, we'll get x equals 3/2. We can substitute that back into our original equation to get our y value. When you do that, you will get -1/4. So our point where the slope is 0, C f of c, that turning point that we have guaranteed by Rolle's theorem is at 3/2, -1/4. So that would be this point right here. Cool. Moving on to the mean value theorem. This uses our endpoints to also talk about the derivative at a point for a function that's differentiable, or you can take the derivative of everywhere between those endpoints. So this says that if we look at the secant line, aka the slope of our secant line, aka our average rate of change on the interval, then it must be equal to our instantaneous rate of change at some point on that interval. Instantaneous. Went off a little bit. All right. So that means if we were to find our slope, we can set that equal to our derivative and find a point where our derivative is equal to the slope of the secant line. So we're going to do just that. So we're considering this function 5 minus 4 over x, and we're looking at the open interval 1 to 4. So we're going to have to find f of 1 and f of 4 in order to find that average rate of change. So f of 1 would be 5 minus 4 divided by 1, or 1. And f of 4 would be 5 minus 4 divided by 4, or 4. All right. And we also need our derivative. So before we can get that derivative, we're going to have to rewrite our function with a negative exponent. So that means to bring that x up top, we have to make it x to the -1. All right, so now that we've done that, we can find our derivative. Our derivative of 5 is 0 for our exponent. We're going to use the power rule, so bring down that exponent, make it 1 smaller. So we get -1 times 4, which is 4, divided by x squared is our derivative. All right, so let's use this equation on the right. We don't know c, that's what we're interested in finding, right? We're finding all values of c. All right. So then we have to find our average rate of change. So 4 minus 1 over 4 minus 1, or 3 over 3, or 1. So we're looking for when the function 5 minus 4 over x I'm sorry, my derivative, yikes. My derivative is 4 over x squared equals 3 over 3, or 4 over x squared equals 1. We multiply both sides by x squared. We've got x squared equals 4. Do the square root. You have to include your plus or minus there. So we've got x equals positive or negative 2. Which points are on my interval? My interval is from 1 to 4. So the only value of c is going to be positive 2. Right? Negative 2 is not between 1 and 4. And we're all good. Now let's look at a practical example. So we have 2 cops. They're stationary. They're equipped with radar, and they're 5 miles apart. All right, we've got this nice little diagram below. A truck passes the first patrol car, and its speed is 55 miles an hour. 4 minutes later, the truck passes a second patrol car, and its speed is 50 miles per hour. Prove that the truck must have exceeded the speed limit of 55 miles an hour at some time during the 4 minutes. So we're saying, well, the instantaneous rate of change at some time on that interval had to be greater than exceeded, so just greater than 55. So to draw conclusions about the derivative on the interval, we're going to use the mean value theorem and think about our average rate of change, because we know that our average rate of change is going to tell us about our derivative on the interval. So when we're talking about position, we normally use s, so I'm going to substitute that in for my f. So in this case, our endpoints, we start at t equals 0 and we end at t equals 4. Right? But we're interested in having our speed in miles per hour. So we need to convert our B and A to hours. So if we've got 4 minutes, we divide by 60 to get hours. 4 over 60 is the same as 1 over 15. So I've got my starting time of t equals 0 and my end time of 1/15 of an hour. So now we're going to go ahead and do that 5 miles. Right, that's the distance we travel, is 5 from our starting point of 0. And we have the time we get to the 5 miles, 1/15 minus 0. The position, the time when we started. So we've got 5 divided by 1/15. Multiplied by the reciprocal, you've got 5 times 15 over 1, which is going to give you a guarantee that you have the derivative, or the instantaneous rate of change, that would be in miles per hour. All right, of 5 times 15, which is 75, somewhere on that interval. So we, at somewhere on that interval, are guaranteed to have a speed of 75 miles per hour, which is faster than the 55. So we've just proven that even though we're going slower than, we're going a maximum of 55 at those 2 endpoints, somewhere in the middle, our truck was speeding along at 75 miles an hour.